we're going to look at something kind of unique. It's called polar coordinates. Polar coordinates can fit in almost anywhere in a calculus course, Calc 1, 2, or 3. It's kind of independent of everything else. And this is a good place to do it because we just finished parametric equations, which give you a different way of expressing points in a plane than what you're used to. And polar coordinates is something akin to that. So I have here drawn a XY coordinate system. Here's your x-axis, there's your y-axis, named after Descartes, who was the one who kind of came up with the way of relating geometric figures to mathematical equations. And so, as I was just saying before I got cut off by my computer, so this is the second time around, if you take any point on the plane, that point has a unique address. Here's a point right there. It's the point 68 because you move 1, 2, 3, 4, 5, 6 units in the positive x direction, and then 1, 2, 3, 4, 5, 6, 7, 8 units up in the positive y direction. So every point has a unique address, and every address corresponds to a unique point. So as I say, that works quite well for lots of things. But there are situations where a different way of addressing the points works better, and so let's look at and see what that would be. Here's the way. It's called polar coordinates. And in polar coordinates, instead of giving the x-coordinate and the y-coordinate, instead you give the distance from the origin. Let's call it r. We'll call it r because everyone else does. That's the distance from the origin. And then the other thing that you need in order to be able to arrive at that particular point is the angle theta. Theta is always taken as an angle from the positive x-axis. And if you go in the counterclockwise direction, it's considered positive. If you go in the clockwise direction, it's considered negative. So anyway, so there's another way to express it. You can express it as r and theta. And so in this case, if you were to figure out what r is, I guess that's pretty easy because Pythagorean theorem tells you here's a 3, 4, 5 triangle. It would be 6 and 8, and so this would be 10. So the point 6, 8 in rectangular coordinates would correspond to 10, and then what would the angle be? I think it's around 53 degrees actually. If you take the let's go ahead and do it. Let's see. So how can we do it? We can say this is 8 over 10. So we will take the arc sine of 0.8. So here's 0.8 and arc sine 53. Yep, I just happen to remember that. 53 and it gives it to me in degrees. If I multiply, well, I'll just write it as 53 degrees. Okay, typically I would write that in radians. I guess maybe I better. So I'm going to multiply it by pi. Pi times 180 divide, and it's 0.93 roughly, approximately. So 93 radians. Okay, so there's the polar coordinate, there's the rectangular coordinate. So that's another way of getting there. Now, first thing you should notice is that polar coordinates is not quite as handy as rectangular coordinates for the following reason. As I say, rectangular coordinates, there's only one way to express this point right here, and that's the point 6,8, coordinate 6,8. With polar coordinates, I can either call it this one, or I could also call it this one plus 2 pi, right? Because this angle here, there's 0.93 radians, and there's another 2 pi radians. So that would also give me this point. So there's more than one way of expressing it. One other way of expressing it, which I think is important, I'll mention it right off the bat here, is that you can go this angle, which is going to be negative, or, well, actually, we don't even have to go negative. We can do this. I think I prefer this one. We can go this angle here, which is going to be 0.93 plus pi, agreed? If I take 0.93, that gets me right there. If I add another pi, I'm going to be right there. And then if you have a positive radius, that positive radius means you always go in the direction of the angle. So here I start right here. Here's the angle, 0.93 plus pi. And so I start right there, and there's the angle, so I go in that direction. 10 units would end me up right there. On the other hand, if I put a negative 10 there, then instead of going in this angle, I'm going to go in the opposite direction, so that'll end me back right up there again. Okay, so let me say it again. With polar coordinates, you don't think of this as being negative area and this as being positive or anything. Instead, it's if you go in the direction of the angle, that's your positive. If you go in the opposite direction, that's going to be negative. So the point is, there are lots of ways to express it. So maybe one thing we should do right off the bat is we should come up with a way to go from one coordinate system to the other. If you have something in terms of r and theta, so here's r and theta right there. Let's go ahead and just get that back again. Okay. Then what is x? What's the x coordinate in terms of r and theta? Notice that this is x right here. So x over r, adjacent over hypotenuse is the cosine of theta. So x over r is equal to cosine theta, which means that x is equal to r cosine theta. And similarly, y over r, here's y over r, is equal to the sine of theta. And so that means that y is equal to r times the sine of theta. Okay, so those are ways, if you know the polar coordinates, those are ways to get to your rectangular coordinates. If you have your rectangular coordinates, how do you get the polar? Well, it's easy enough to get r. R is just going to be what? The square root of x squared plus y squared. That's Pythagorean's theorem, so that's easy enough to get. How do we get theta? If you have y and x, then I guess the tangent of theta is equal to y over x, which tells us that theta is the arctangent of y over x. Okay? So you've got those ways to go from one to another. Okay? Very good. So I'm going to kind of do the same thing I've been doing in Calc II. I'm not going to just give lots of examples of these things. You can find examples or come up with your own examples. Maybe one that might be kind of important is this one right here, just by way of a quick one. Let's see. What if we say this is a 30 degrees? Let's make this equal to 10 again. And let's say that this is 30 degrees. 30 degrees is the same as pi over 6. And so there you have that. And so the y coordinate would be 10 times the sine of pi over 6, which is equal to 1/2. Which is equal to 5. And the y coordinate is going to be 10 times the cosine of pi over 6, which is 10 times, what's the cosine of pi over 6? Square root of 3 over 2. So it's going to be, what, 5 times the square root of 3. Okay, so there's a couple examples. Now, as I say, there's some good reasons for wanting to do things in polar coordinates, and one of the most important is that you can graph some things very nicely. First of all, just to be really obvious, a circle. Let's take the circle of radius 3. There's a circle of radius 3. If you were to write it in rectangular coordinates, you would say what? X squared plus y squared is equal to 9, equal to r squared. Okay, but in polar coordinates, it's just r is equal to 3. Boom, that's all there is to it. Because it's kind of analogous to a line like this. Here's the line y equals 2, and it's just the constant line. Here would be r equals 3, so it gives you that circle right there. So there's some that are very easy like that. Let's do some other ones and just see what they graph to. I'm going to do several that are quite important. So let's first take r is equal to 2 cosine theta. Okay, 2 cosine theta. What does that graph into if we were to graph it? Well, here's the way I like to do it. I like to make a little table here. Here's theta and here's r. And then I like to take the easiest points of theta to use. And so those are the places where I know that the cosine is either 0 or 1. If theta is equal to 0, the cosine of 0 is 1. 1 times 2 is 2. So then the radius is 2. If the theta is pi over 2, the cosine of pi over 2 is 0. By the time you get to pi, the cosine of pi is negative 2. 3 pi over 2, the cosine of that is 0, and if you go back to 2 pi, you're back to 2 again. Okay, so those are easy points to plot. What do they plot into? Well, let's do it. When the angle is 0, here's your angle 0, you're a distance 2 out from the origin. I think of this as like a boy and his dog. I think of it as like a dog who's on a rope, and the boy is at the origin, and he holds the leash of the rope, and he pulls the dog in or lets the dog out. So as the dog is running from here to pi over 2, the boy is pulling in on the leash, and so the dog is going this way, but as he does it, the boy pulls in on the leash so that by the time he gets to pi over 2, this angle, it's 0. Now, what happens as you go from pi over 2 to pi? Now the radius goes from 0 to negative 2. If it went from 0 to 2, you'd go out like this again, but it's going from 0 to negative 2, so instead of these values, it's the opposite, so it's going to be in this direction, and it's going to end up something like that. When you go to 3 pi over 2, I'll let you figure it out, but you're going to just retrace that again. Now, the way I drew that, it looks like it could be a circle. Who knows though, maybe I drew it all wrong. All we know is it goes through this point and this point, but it might not be a nice circle. Let me prove to you that it is. Okay, I'm going to prove to you that it is. Watch this. I'm going to multiply both sides by r. Agreed I can do that? Then I'm going to put it in terms of rectangular coordinates. R squared is equal to x squared plus y squared. And then this is going to be 2x right here, right? Because our cosine theta is x. And so now I can write x squared minus 2x plus y squared is equal to 0. And now, if you remember this from pre-calculus, you can complete the square. X squared minus 2x, you take half of negative 2, which is negative 1, and then you square it, and you get 1. So I'm going to add a 1 right there. If I add it to that side, I'm going to have to add it to this side. The y, there's no y's in there. I just have a y squared, so I get that. And now the reason for doing this is that now I can write this as the quantity x minus 1 quantity squared plus y squared is equal to, I'll write it as 1 squared. And if you remember from pre-calculus, that is, oh, I shouldn't have erased it. That is the equation of a circle which is centered at 1, 0, right there, and with radius 1. So there it is right there. So there's the circle of radius 1 centered at the point 1, 0. Okay? So there's that one. Let's make things a little more interesting. Let's make it what did I have there? 2 times the cosine of 2 theta. How's that going to change things? How's that going to change things? I tell you what, before we do that one, let's go back to this other one, and let's this one's going to be a little easier. Let's make it 3 plus 2 cosine theta. Let's see what we get here. So so I'll erase this, and let's just put in the numbers again. Let's see, if theta is 0, you're going to get 2 plus 3 is 5. Here, this is going to be 0 plus 3 is 3. When it's pi, this is going to be -2. -2 plus 3 is 1. By the time you get back to 3 pi over 2, it's going to be 0, 3, and back to 5 again. So there's your 5 important points. Let's graph them and see kind of what they look like. When the theta is 0, you're here at 5. By the time the dog is run to pi over 2, you've pulled in on the leash. So now it's at 3, like that. By the time the dog gets to pi, the boy is pulled in on the leash, and so you just have a length of 1. And pi is in this direction, so it's going to be positive. It's in the direction of the angle, which is 1. By the time you get to 3 pi over 2, you're back to 3 again. And by the time you get to 2 pi, you're back to 5. So this thing is going to look kind of like this. And you can easily go to Google or whatever, find some math software to graph you some really nice pictures of these kinds of things. But there you go. You should understand why they look like they do and just have a general sense of what they look like. Okay? What if instead of a 2 here, let's make this a 2. Let's go like this. Do it like that. How's that going to change things? Now this will be a 4. This will be a 2. This will be a -2 plus 2 is 0. This will be back to 2 again, and then this will be back to 4. So it's going to have the same general shape, but instead of being 1 out here, it's going to, first of all, this is, well, let me just redo the whole thing. It's going to start at 4. It's going to go to 2. By the time your angle gets to pi, it's going to come all the way in to 0. It's going to come in and touch the origin. See that? And then when you leave, it's going to leave the origin like this and then come back like that. Do you see why that particular shape is called the cardioid? Cardioid, as in cardiac arrest, right? Heart. It has the shape of a heart. So there's that one. Let's do one more. What if this were a 3 right here? How would that change things? This is where, if you've been following along, just kind of watching, at this point I want you to take a minute and turn off the computer and try to figure it out on your own. See if you get it right. I want you to do it because I've taught this class dozens of times and very few people get this one right. So you can consider it a challenge and see if you do or not. Okay? Okay, hopefully you're back again. Let's go ahead and do it together. You're going to start off at 5. By the time you get to pi over 2, this is going to be 0, so it's just going to be 2. By the time you get to pi, this is going to be -3 plus 2 is a -1. See that? That's what's different. Then back to 2 again, and then back to 5 again. Okay? So hopefully you got that. The real challenge is, what's the graph going to look like? It's going to go through 1, 2, 3, 4, 5. It's going to go through there. It's going to hit this point. By the time you get to pi, see this? By the time you get to pi, it's going to be at -1, which means instead of being in this direction, it's going to be in this direction. So it's going to hit that point. Okay, you're back again. And by the time you get to 3 pi over 2, you're back here again. And by the time you get to 2 pi, you're back there again. Okay, so again, I'm going to give you a moment to try to figure out what this graph looks like. And here's the challenge. See if you can do it right. But don't watch me. Try to do it first. Okay, turn it off. Okay, hopefully you're back again. Okay, let's see once what happens. You start here. You go there. Now, as the angle goes from here to here, you're going to end up at -1. So this is what lots and lots of students do. They go like this. They draw it in kind of like that. Why is that wrong? It's wrong because as the angle goes from here to here, the radius is going to go continuously from values of 2 to values of -1. It's going to hit all the values in between. If it hits all the values in between there, in particular, it's got to hit 0. So let's think about it. Here's your angle. It's going like this. As your angle goes like this, you're starting at 2. You're going to eventually hit 0. And then once you hit 0, you're going to continue going to -1. Now, your angle is still here, but now you're taking on negative numbers, so you're going to end up like that. And then here's what the rest of it looks like that. Okay, so 3 cheers if you got that right. Okay, let's try 2 more I want to do. Let's do 3 times, or let's make it 5 just to make it a little bit different. 5, okay, that's fine, times the cosine of 3 theta. 5 times the cosine of 3 theta. Oh, let's first make it 2 theta. Okay, 2 theta. Okay, here's the way you do it. So let me show you a really nice scheme for doing this. You put the 2 theta right here, because that's what you're taking the cosine of. Here's your r right there, and then you put your theta right there. Because ultimately, we're going to say, given that this is the theta, what's the r going to be? But let me show you why this is a nice way to do it. Again, you want to take the cosine of nice numbers. So the nice numbers that I want to take cosine of are going to be the numbers 0, pi over 2, pi, 3 pi over 2, 2 pi. What's the next one? 5 pi over 2, 3 pi, 7 pi over 2, and 4 pi. Okay, and you'll see why I have to go through all those. First of all, if that's what 2 theta is, then theta is going to be half of it. So theta is going to be 0, pi over 4, pi over 2, 3 pi over 4, pi, 5 pi over 4, 3 pi over 2, 7 pi over 4, and 2 pi. See that? I just divided all these by 2 to get these. So these are your angles. Okay, these are the nice angles. That's the ones that we're going to be able to take the cosine of. But these are the angles going all the way around the circle that we're going to have to take into account. And then finally, we need to, of course, find out what the value of the function is for all these. And this we've already done before. The cosine of 0 is 1, so 1 times 5 is 5, so that's going to be 5. When 2 theta, when this angle right here is pi over 2, what's the cosine of pi over 2? It's 0. 0 times 5 is 0. What happens when 2 theta, that's this angle right here, what happens when 2 theta is equal to pi? The cosine of pi is equal to -1, so that's going to be -5. Then 0, then 5, 0, -5, 0, and 5. Okay? You check all those out. So now, what happens as we go around? First of all, we should kind of sketch in these angles here. Pi over 4, that's 45 degrees, so that looks kind of like this. And then here's 7 pi, here's 3 pi over 4. Okay, there they all are. So what happens? When the angle is 0, the radius starts at 5. 1, 2, 3, 4, 5, right there. By the time the angle gets to pi over 4, which is right here, the radius goes to 0. So it goes to 0. By the time the angle gets to pi over 2, here's pi over 2 right here, the radius goes to -5. Okay, if it went to +5, you just go straight up there, but it's going to -5, which means I go down here instead. Now, by the time you get to 3 pi over 4, which is right here, the angle goes back, the radius goes back to 0. So it starts at -5, and it's going to be the negatives of all these, so it's going to start down there and go back to 0. Now, going to pi, here's the angle going to pi, the radius is going to go back to 5 again. That goes in the direction of 5. By the time you get to 5 pi over 4, it goes back to 0. By the time you get to 3 pi over 2, so that's right from here to here, it's gone to -5 again, and then back to 0 again, and then finally, let you finish it off, it looks like that. So it's a four colored, I can't remember what the name of them are. But anyway, it's a four petaled flower. Okay, and again, there's much nicer ones on the internet. Okay, the last one I want to do is what happens if we change that to a 3 rather than a 2. And I will just give you the answer. You have to go through the same thing, except now this is going to be 3 theta. And so 3 theta has got to take on all these values. And so theta is going to be each of these things divided by 3. Okay? So this is going to be pi over 6, pi over 3, pi over 2, 2 pi over 3, 5 pi over 6, pi, 7 pi over 6, 4 pi over 3. Divide everything through by 3. And so the angles that we're interested in are now the angles like pi over 6, which is like this, pi over 3, which is like this. Those should all be the same angle, kind of like this. This, roughly like that. And I'm going to do it a little more quickly here, and you can fill in the details. When theta is 0, r is going to be 5. 1, 2, 3, 4, 5, so it's going to be right there. By the time you get to pi over 6, it's going to go to 0. So here's pi over 6, it's gone to 0. By the time you get to pi over 3, which is right here, it goes to negative 5. If it went to positive 5, it would be out here, but it's going to negative 5. So it's going to go like this. Then back to 0 again. This is your negative axis here. Then back to 0. Then by the time you go to 2 pi over 3, it goes to 5. So here's 2 pi over 3 right there. Then back to 0 again, like that. Then to negative 5, so it goes right there. And then, if you keep continuing on, you'll notice that unlike when you had a 2 here, this one just repeats everything again. So you just keep going on. That's why I didn't go any farther here, but you're going to end up doing the whole thing one more time. So the moral of the story is when you have an odd number here, you end up with that same number of petals on your flower. If you have an even number, then you get twice as many. Okay? So that's the idea. Okay, how are we doing? 31 minutes. I'm not going to have too much to say about finding the areas of things, so I'm just going to throw that in on the same lecture here. Because that's another thing that you want to be able to do if you have some object written in polar coordinates. So say we've got some sort of a function like this, and instead of being a function of x and y, it's a function where r is a function of theta. Okay, like all these were, right? Theta is the thing you stick in, and then r is the functional value. So we've got something like this. Well, go back to how we found areas under curves. Areas under curves, what did we do? We added up a whole bunch of little rectangles, agreed? This was a little dx right there, and the height of it was f of x. And so we took the height times the thickness, and we added them all up, and that gave us the area. Now we're going to do something similar, except now we're not adding up rectangles. We are moving like this, right? Where the theta is moving, and then the r moves as theta moves. So we're not adding up a whole bunch of little rectangles now. We're adding up something more closely related to triangles. See that? It's basically, it looks pretty close to a triangle. And so if you think what the area of a triangle is, it's closer and closer to a triangle as you take smaller and smaller little angles there. What's the area of a triangle? Area of a triangle is 1/2 the base times the height. Agreed? And so we're going to do something similar here. We're going to say, okay, for a particular theta here, the height is going to be r, and now I have to multiply that by this base. First of all, it's going to be 1/2 the height times the base. So here's 1/2. There's the height of it. And now what's the base? Remember this? It's basically very much related to, you can think of it as being like a sector, I guess. I'm being a little bit sloppy here. Sometimes I'm thinking of it like a triangle. Sometimes I'm thinking of it kind of like a sector. But the point is, what's the relationship between r and theta and s? Remember what we learned in trigonometry? That s is equal to r times theta. So this little distance right there, if this is a tiny little d theta right there, if that's a tiny little change in theta, then this distance right here is going to be r times that little d theta. And so this is the length of the base, this is your height, and then there's your 1/2. And if you just add all those things up, as you start at one angle, theta 1, and end up at theta 2, you're going to get the area of a polar coordinate graph. And when I say the area, what I mean is it's the area in the region starting at the origin and starting at whatever angle you start at and going to whatever angle you end up at. Okay? So, heck, should we do one? Let's just go ahead and do one. I'm gonna give you an interesting one. Okay, here's a really interesting one to do. This is one that, again, if you're in my class, you're gonna see this problem. Here's the circle r equals 1. There is the circle centered at the point 1, 0 with radius 1. We just did that one a few minutes ago. And then finally, you got this one here, centered at that. Okay, so there's 3 circles. And notice those 3 circles have produce a nice little region right there, which is outside of this one, and it's kind of contained by those 2 right there. And so a really nice problem for you to do is to try to figure out what's the area of that little region right there. Okay, and I'm going to leave it right there. So you need to kind of take what we did with area and run with it, but find out what that area is. I've never seen this problem in any calculus book, but it's a beautiful one. Okay, simple to state, kind of elegant. Find the region of that little almost looks triangular right there. Okay, very good. So that's polar coordinates right there. That's everything you need to know.